In this lesson, we're going to look at implicit differentiation. And that's used when you have y given implicitly as a function of x. Here's what this means. Here on the left, we have a function y solved for x. Y is solved explicitly for x. So what this means is that y is all by itself on one side, and x is around the other side with no y's. And the idea here is that if I need to figure out what a value y is, I just plug in an x. If I need to know, say what is y when x is 2, I can just plug in x equals 2, and it tells me y equals 8 minus 2 is 6. So here y is solved explicitly for x. In this equation here, y depends upon x implicitly, and that's the phrase that is used. And all that means is that if you look at the graph of this curve here, and there's no reason you would know that this equation has this graph. I just looked it up online. It's kind of a pretty looking graph. What this means is that if you're at some point along this curve, maybe you're here, you're at some particular x, y. If you change x, y has to change to stay on the curve. So y depends on x. Y is not constant with respect to x. If x changes, y has to change if you're going to remain on the curve. But this is not solved for y. If I want to know, let's say, what is y when x is 1, I have to solve the equation and figure out what y would be if x were 1. And this is, nevertheless, we can use calculus techniques in order to determine things like slopes of tangent lines and things to graphs like this that are not functions of y. And you know this is not a function of y. It fails the vertical line test in several places. But we can still use calculus to figure out, say, what's the slope of the tangent line at any particular point along the curve. What implicit differentiation is, when you're taking derivative, is really it's just a clever application of the chain rule. So let's look at some examples here. Let's say I had to take the derivative of sine of x cubed. So we know how the chain rule works now. We think of this as being u, I'll write it in really lightly, u to the third power. So the derivative would be 3u squared, but u is sine x. And then I would multiply by u prime. That's the derivative of the thing in here. The derivative of sine is cosine. So I get cosine x. And that would be the derivative of sine of x cubed. What if I didn't know what the function inside was? What if I was just said I want the derivative of f of x cubed? Well, I use the same procedure. I think of this as some sort of u, and I get 3u squared. So now this is 3f of x squared. And then I multiply by the derivative of the function inside. But here, all I have is the function named by f of x. I don't know its derivative, so I write it symbolically. I say, okay, well, whatever f is, the way I write its derivative is I write f prime of x. And that idea is going to be used in implicit differentiation. Let's say I want to take the derivative with respect to x of y cubed. And I know from context that y here is not a constant with respect to x. In other words, if x changes, y has to change, but it changes in an unspecified way. I don't know exactly how y explicitly depends on x. I use the chain rule to compute this derivative. In fact, this is exactly the same as this. Here the unknown function is called f of x. Here the unknown function is called y. Y depends on x, so y is a function of x. So I use the chain rule. I go, okay, well this would be 3y squared. And then since y is a mystery function of x, I say I have to use the chain rule and I multiply by the derivative of that y, and I don't know what that is. And so I just write it symbolically. I write times dy dx. Whatever y is, its derivative is going to go right there. And when you're doing implicit differentiation, it's advisable, because you're writing so many of these things, to write y prime. Make sure your primes are nice and slanted so they don't look like a first power. How would it work for an expression like this? Let's say I know, again here, y is not a constant. Y depends in some sense on x, so I'm going to have to use implicit differentiation. So first, I recognize this is a product. This is x times y squared. So I'm going to use the product rule. So I'm going to have d dx x times y squared. plus x times d dx y squared. Now this first term, there's no implicit differentiation. D dx x is just 1. So I'm going to get 1 times y squared, which of course I would normally write as y squared. But on the second term, I have x times d dx y squared. So here's where the chain rule, the implicit differentiation, is going to come into play. If this were d dx x squared, I would just write 2x, and I would be finished. But since it's d dx some other function squared, I write 2y, and then the chain rule tells me I have to multiply by the derivative of this hidden function inside here, like here, when I had to multiply by the derivative of sine. I don't know what the derivative of this function is, so I just write it symbolically. I say times its derivative, times y prime. One last example. Here's a 3-term example. So we know derivatives go term by term. So the derivative of this, there's no y's in here. This is just a straightforward 3x squared. So I take its derivative, I get 6x minus. Now this is a product. This is 2x times y. So I'm going to use the product rule here. So I'm going to have 2 terms coming from this. So I have the derivative of a is 2 times b. We put parentheses around there because I have to subtract both terms that I get from the product rule since there's a minus on this term. And then I'm going to have the derivative of b. Now this is d dxy, so I don't, again, that's just y prime. That's the derivative of y with respect to x, which I'm abbreviating y prime. And then I have times the 2x from the chain rule, or from the product rule. So there's the product rule on this term. Then I go to the final term, the derivative of 7 root y. This is, remember this means 7y to the 1/2. And so when I take the derivative of something to the 1/2, I bring the power down in front, so I get 7 times 1/2 y, then I subtract 1. And then I have to multiply it by the derivative of the function inside. This is not x. If this were d dx x to the 1/2, then I would be finished. But since it's y, I have to multiply by y prime. So let's see this used in a typical application of this. Something like the initial curve. I had to fiddle around to find a curve that worked well. So I've seen many AP problems that look very similar to this. So let C be the curve given by x cubed plus y cubed minus 12xy equals -10. So I have no idea what this curve looks like. I'd have to use software to figure out what this looks like. But you don't need to know what this looks like in order to do these parts of this problem below. So part A. First, we're going to show 1, 1 is on the curve. Well, that just means plug 1, 1 into this and show it satisfies the equation. Both sides will be equal. So I get 1 cubed plus 1 cubed minus 12 times 1 equals -10. And this is true. And so that means C is on the curve. This is 1 plus 1 minus 12. So now I'm going to compute dy dx for C. So I'm going to take this curve and I'm going to compute its derivative. So what you do is you say, well, if these two sides are the same, for every x and y, these are the exact same on either side. That means if I take the derivative, they're the same. So I take the derivative of both sides of this equation. I'll write out. I'll say, okay, so I'm going to take the derivative of the big, long, messy left side. And then I'm going to take the derivative of the very straightforward right side. The right side is straightforward. That's the derivative of a constant function, so this is going to be 0. The left side, I have 3 terms. So, d dx x cubed, this is ordinary derivatives, no implicit differentiation here, there's no y's, so this is just 3x squared plus. Then I have d dx y cubed. This is very much like this. I get 3y squared, But since this now is a function of x that I don't know, the chain rule makes me multiply by its derivative, which I'll abbreviate y prime. Then I have a product. I have minus, this is going to be my part A from the product rule, this is going to be my B from the product rule. So the derivative of A is 12 times B, which is y, plus, then I have the derivative of B, that's d dx of y, so it's simply y prime, times 12x. On the other side, I have the derivative of the constant function of minus 10, so that is 0. So the problem is asking me to figure out what dy dx, and remember we're just using y prime for shorthand. So now this is algebra. I have to solve this for y prime. And it's a fairly standard procedure. First we're going to clear out these parentheses. So the minus distributes across the parentheses. And once you've done that, I'll rewrite this as minus 12x y prime. I always like to put things in alphabetical order with the y primes last. Once you've done this, you identify, we got 4 terms, 3x squared plus 3y squared y prime minus 12y minus 12x y prime. We identify the terms that have y prime, and we identify the terms that don't have y prime, and we put them on opposite sides of the equation. So these two terms here, this term and this term, I'm going to subtract across to the other side of the equation, because these don't have y prime. These do, so I'm going to leave them on this side of the equation, on the left. So on the left I'll have 3y squared y prime minus 12x y prime, and on the right these two terms will subtract across. This one will become positive, I'll get 12y. This one will become negative, minus 3x. Then I can take this y prime on these two terms and factor it out. 3y squared minus 12x. This equals 12y minus 3x. And then I can divide by this factor on the y prime, and I get y prime equals 12y minus 3x squared, which was over here, divided by 3y squared minus 12x. And I notice that top and bottom are multiples of 3, so I'm going to multiply top and bottom by a third just to make things a little bit nicer. So this is 4y minus x squared over y squared minus 4x. And this is the answer. You may be thinking, well, that's horrible. What do we do with all those y's? And the answer is we leave them there. What this is telling me that the derivative, you not only need to know the value of x, but you also need to know the value of y to compute the derivative. And the reason for this, I mean, I don't know exactly what this looked like, but let me go back to that first curve that we looked at. Okay. This curve here, which is similar to this one, isn't a function. So just by knowing the x value, you don't know where you are on the curve. You need to be told both the x and the y coordinates in order to figure out what the slope is, because the slope at these different x coordinates, or these different y values for each x, could be different. That's why your expression for the derivative here contains both x's and y's. You need to know both the x and the y coordinate of your point on this curve in order to get the derivative. So, and now we're just going to use this expression that we've created here for y prime. The last part says, determine an equation of the line tangent to C at 1, 1. Notice we've already verified 1, 1's actually on the curve, so it makes sense to talk about a tangent line to C at that point. Well, we already have the point, so we just need to know the slope of the tangent line, and that's going to come from y prime. Excuse me. Y prime gives slope of tangent line. So y prime at 1, 1, this is the notation, so we're going to plug in 1, 1 into this. So we're going to put x equals 1 and y equals 1 in this expression up here is 4 times 1 minus 1 squared over 1 squared minus 4 times 1. So what is this? This is 4 minus 1, 3 on the top. And this is 1 minus 4, negative 3 on the bottom. So this simplifies to negative 1. So the slope of the tangent line is negative 1. So that means my tangent line looks like this. I have y minus 1, the y coordinate on the line. I have x minus 1, the x coordinate on the line, and then the slope is minus 1. There's the equation of the tangent line to the curve above at the point 1, 1.